Okay, logarithms. Now this is a big day. Seems like a really boring worksheet. Actually, I might want to add some spaces within this. I don't know if the square box matters, but this is a big day. This is all about logarithms, and I teach more than is necessary just for the homework. So even though it's a simple, empty worksheet, this is an important one to pay attention to. Okay, fine. Let's start with what we know. You have graphed this parent function before, so why don't you hit pause and just go ahead and I'll do it in green. Go ahead and do yours, and then come back and I'll do mine. Okay. Okay, I'm doing mine now. When we did 2 to the x power, remember x can be anything. We like x is 0 because that's nice. We had, if I do in this order, 1, 2, 3, that's nice and balanced. What was the special point where x is raised to? I call that my anchor point. And anything to the 0 power is 1. And so 2 to the negative 1, of course, is 1/2, 1/4, and 1/8. And when we made a graph over here, it's really, really close, and it's pretty close, and then it's 1/2, and then it's 1. And of course, 2 to the 1 is 2, 4, 8. 2, 4, that'll be 5, and then that'll be 8 right here. Okay. Easy to get my parent function for exponent. There's a reason we're doing this, because I'll do it in blue. A log is an inverse of an exponential, and that's why we're doing this. Okay, but let me finish up with my properties for my logs. My domain for my exponential y equals 2 to the x parent graph was all real numbers. The range is from 0 to infinity. Parentheses, what's its shape? Well, it's exponentially. The x-intercept, none. My y-intercept was the point 0, 1. In behavior, as this silly little cut and paste here, as x goes to positive infinity, f of x is going up to positive infinity. As x goes to negative infinity, I like to have negative on this side, but oh well, I'll just go with the format. As x goes to negative infinity, f of x is going to my asymptote, which in this case is y equals 0. Okay, it is increasing over the entire domain of all real numbers, and it is never decreasing. Not applicable. Okay, simple enough. Now, I'll do my, well, if a log is an inverse, can you all graph the inverse of this function? I mean, let's just use that. If a logarithm is an inverse, in other words, the logarithm undoes the work of an exponential, then how could you quickly graph the inverse or graph the log graph? I don't even know what the function is, but you can graph it. Hopefully the clever amongst you said, well, I just basically swap x and y. I remember last unit, the one we should have taken a quiz or test on, but didn't. So if I swap x and y, and for my logs, this becomes my x column, and this becomes the y equals the log of x column, well, then I should be able to, if x is 1/8, y is -3. Okay, I can do that. If x is 1/4, it's -2, and then 1 and 0, and then 2 and 1, and 4 and 2, and 8. So 5 is here, so 8 is 3. I can connect these dots. I'll connect these dots. And lo and behold, just like it was last unit, if I were to fold the paper along the red dotted line, the green line and the blue line would fold over on top of one another, and that's exactly reflection across the line y equals x is what makes an inverse. So the blue is a log graph. Okay. Well, let's look at our properties of this graph. What is the domain? It looks like the domain of the blue graph, which is my log graph, I know the graph, but I just don't know the equation yet. If I look at that graph, then fine, that goes from, let me do it in blue, 0 to infinity. Here, the range appears to be going all the way down to negative infinity, all the way up to positive infinity, eventually up this way, so it's all real numbers. What's the shape? I don't know. It has a vertical asymptote. So we'll call it log. I'll just make it some name. Is there a x-intercept? Indeed there is. It is the point 1, 0. Is there a y-intercept? Nope. What's the end behavior? As x goes to infinity, what's my y value go to infinity? As x goes to negative infinity, it doesn't apply. It's a not applicable. Let me close my door. I got dogs barking outside. Okay. As increasing, is it increasing? Yes, it's actually a positive slope over the full domain, but the domain in this case is from 0 to infinity. And is it ever decreasing? No, never decreasing. So what do I notice on this? For the important pieces like domain and range and etc., notice that the role of the green and the blue are swapping roles, as indeed they should from swapping x and y here. So what is my equation? What is the equation of f negative 1 of x, my inverse function? I don't know. Do we remember our two-step process? Step 1. What do? We swapped x and y, right? So if I do that on my parent function, that would become x is equal to 2 to the y power. All right. Step 2 was solve for new y. How do I do that? Looks like I put that on my thing. How? Well, indeed, that is exactly what we need to learn how to do. So we're going to basically take the liberties that only a mathematician can. I'm going to invent a log function because I can. A log, well, I'm going to call that function. And throughout this thing, notice that we're trying to solve for this y, correct? And y is a power. So as we do this, it's very important to remember a log is a power. I don't know. I'll circle that and put pink stars around it. That's a really important. It has all the properties of a power. We'll see that as we go through this. A log is a power and has all those properties. So let me invent this new function for us. I'll do it in purple. Y is equal to the log base b of x. I didn't do it in purple, did I? I did it in green. So when I say that, I will map it. Maps to. Remember how it's an inverse function of an exponential? I kind of want to look at this as being the inverse of an exponential form over here, but recognizing that the y is a power because a log is a power. The logarithm function here yields me a power y. And I remember b is the base for my exponential form. So how would I map that? Well, this b right here raised to the y power will get me back to x. So what color? Now I'll use purple. B to the y power will get me back to x. And mapping between logarithmic form and exponential form is an excellent way to solve these things. Might seem weird to just invent a random function like this, but it is useful and I can do it. Okay, hopefully you're caught up. Actually, the nice thing about YouTube is you can pause if you want to catch up, taking notes down. Okay, well, let's look at an example. It'll make it easier for me. Let's work with powers of 10 because those are nice. Y equals the log base 10 of 100. Let's do the little mapping thing. That arrows both ways. I'm just using that as an indication of map. Maps it to. Okay, how would I map this into my purple exponential form? Well, notice, where's my mouse? I don't see my mouse anymore. It's acting weird. There we go. It turned into a little dot. Now, there it's back, so you can see it. Up here, notice that the b was raised to the y power. Okay, fine. 10 raised to the y power will be equal to 100. Fine. 10 to the y power equals 100. And hopefully you're going to look at that and say, well, okay, I know. Well, y must be 2 because 10 squared is equal to 100. So y has to be equal to 2. And if I use that knowledge, I'll use pink. Another way to read this that's very helpful is the power, because remember, logs are powers. Y, the logarithm function is a power. The power of 10 to get me 100. If I just look at this thing right here, what it's doing is saying 10 to what power will get me to 100? Well, 2, and y is 2. Okay, I'm going to write a few more down, and I'll have to write these down before you hit pause, but what will be the log base 10 of 1,000 and the log base 10 of just plain old 10? And by the way, if I just write log of 1, this is an important point. It's understood to be base 10. What can I write this? Well, I'll squeeze it in. To be base 10 if blank. Logarithms are usually base 10, so if I just say log of 1, it's understood to be base 10. Important point. Okay, fine. Equals. So I'm just going to write log of 0. And recognize there's an understood 10 here. Log base 10 of 0 is understood. And then we'll just do log base 10, I'll write it this time, of -3. How about that? Okay, fine. See if you can think about what those are. Hit pause, fill them in, and we'll come back in a sec. Okay, I'm back. Hopefully you actually hit pause and did it. And you did the little, maybe you just did the little words here. The power of 10 to get to me 100 was 2. The power of 10 to get me to 1,000. 10 to the third power is 1,000, so that's going to yield 3. 10 to what power is 10? Well, 1. 10 to what power is 1? And well, 0 to any power is 1, or any power to 0, any base to the 0 power, so that should be 0. Now recognize log base 2, log base 4, the base can be anything. We count in base 10 usually, so that's why log base 10 is the most common one, but the base here could be anything. And no matter what the base is, the log base 5.3 of 1 would still be 0, because any number to the 0 power will get me back to 1 here. Now, can I do log base 0? Log base 10 of 0? No, it is undefined. And we can actually see that if we go back up and look at our graph. The log graph here is blue. I didn't know it at the time when I was making this, but that indeed is the log graph. Can I plug in an x is 0? No, because that's an asymptote, vertical asymptote at that point on my graph. Okay, where am I? Same deal here. Think back to the graph. Could you plug in an x is -3? Can 10 be raised to any power to get a negative number? No, it's undefined. Okay, We're at 15 minutes now. I'll tell you, I'm going to break this in two. I'm going to take a quick, actually, here's what I'll do. I'll write out a few more problems and see if you can do them, and then play the other video if you want to keep going on this thing. Log base 2 of 8, what does that equal? Log base 2 of 1 over 32. Cool, that's a good one. The log base 1/3 of 27. And the log base b of b to the x. Okay, write those down, and then I'm going to start up another part 2 video to keep this thing going.